This lecture will complete SN2 reactions. Last video we looked at the steric effects of the substrate. Now we're going to look at the nucleophile. Okay, so a nucleophile is nucleus seeking. It's looking for a center of positive charge. Now a nucleophile can either be negative or neutral. It should have a lone pair or a pi bond to donate. Because the nucleophile is involved in the rate, it will greatly affect the rate of reaction. The stronger the nucleophile, the more effective the reaction. So if we look at two nucleophiles, here we have methoxide, and here we have methanol. Now the methoxide actually has a formal negative and is going to seek positive charge more readily. So it is a better nucleophile. If you look at the relationship between methoxide and methanol, you'll see that methanol is the conjugate acid and methoxide is the base. So as a rule of thumb, a base is always a better nucleophile than the conjugate acid, than its conjugate acid. In class, I related basicity and nucleophilicity. Let's actually separate the two concepts. So basicity is defined as the equilibrium constant for abstraction of a proton. Nucleophilicity is defined as the rate of attack on an electrophilic carbon. In both types of reactions, we form a new bond. For basicity, you form a bond with a hydrogen. In the case of nucleophilicity, you have a new bond to carbon. There are 3 trends for nucleophilicity. The first one is a species with a negative charge is a stronger nucleophile more nucleophilic than a neutral species. So for example, OH minus is a stronger nucleophile than water. SH minus is a stronger nucleophile than H2S. This stems back to what we looked at before, where the base is the stronger nucleophile compared to the conjugate acid. 2. Nucleophilicity decreases from left to right across a period. So as electronegativity increases, nucleophilicity decreases. This is because the more electronegative, the tighter you hold the electrons, and therefore less reactive toward new bonds, toward new bond formation. So if we just look here across the following nucleophiles, you could see N is the strongest, with fluorine being the weakest. Finally, the third trend, nucleophilicity increases down the periodic table. This is because as you increase in size and polarizability, you decrease in electronegativity, and you're more reactive to new bond formation. You're more likely to give up electrons. So if we look at the halogens, I- is better than Br-, which is better than Cl-, which is better than fluorine. So this is for any group or column. So disregard what we talked about with regard to A- in class. Follow these three trends. The more reactive the nucleophile, the greater the rate of the reaction. In keeping with our talking about the nucleophile, the bulkier the nucleophile, the reduced rate of reaction. Here this has to do with sterics and access to the electrophilic carbon. So if I give you methoxide versus tertiary butoxide, the methoxide is less hindered and will be more nucleophilic. Let's finish up looking at the nucleophile and look at the solvent effects. On nucleophilicity, or the strength of the nucleophile. If you have a solvent that is a protic solvent, where it has hydrogens attached to nitrogen or oxygen, it can hydrogen bond. Some protic solvents are water, ethanol, methanol, these solvents can donate H bonds and form a solvent shell around a nucleophile. So for example, here we have I- and methanol. So you can see when I draw my alkyl halide, because the nucleophile is in a solvent shell, it cannot access the substrate. Polar protic solvents decrease nucleophilicity. They decrease the ability to attack an electrophilic carbon. And a polar aprotic solvent, such as acetonitrile, DMF, acetone, these solvents can dissolve a nucleophile because they're polar, but they do not form a solvent shell. So the rate of SN2 is favored by a polar aprotic solvent. There are no hydrogens that can H bond. So if you have an SN2 reaction, methanol versus acetonitrile, the rate of SN2 is faster in acetonitrile. Let's come back to the substrate. And look at the leaving group. In SN2 reactions, okay, the leaving group serves two purposes. The first is that it polarizes the bond between the carbon and the leaving group, making the carbon electrophilic. Second, it leaves with a pair of electrons. Once bonded to the electrophilic carbon. To do this, a good leaving group must be electron withdrawing, this polarizes the carbon leaving group bond, 2, be stable, so once it is left, okay, so it's not a strong base. Okay, so that it would be, if we think in terms of acidity, A- would be stable. And finally, it must be polarizable to stabilize the bimolecular transition state in an SN2 reaction. Here are some common leaving groups. We have Cl-, Br-, I-, sulfonate, sulfate, and phosphate. If you think about your biochemistry, phosphates, you often lose a phosphate in ATP reactions because it's stable on its own. Examples of poor leaving groups: ROH-, OR-, and amides. This is going to conclude our discussion of SN2, and I'll make a video regarding SN1, and then I'll summarize which we choose, SN1 or SN2, based upon these different characteristics.